All right. Hi, all. Good morning. Thank you all for joining us today for our monthly symposium series. And today we are very excited and honored to have Dr. Benjamin Hsiao as our speaker. He's a distinguished professor in chemistry at Stony Brook University. He also serves as the co-founding director for Innovative Global Energy Solutions Center, and he's currently the director for the Center for Advanced Technology and Integrated Electrical Energy Systems at Stony Brook University. Dr. Hsiao received his BS degree in chemical engineering from National Taiwan University. He has a PhD in materials science from the University of Connecticut and a postdoc training in polymer science and engineering at University of Massachusetts. He joined DuPont Company as a staff scientist and spent 8 years in R&D before coming to Stony Brook. He has also served as a chair for the chemistry department, held the vice president for research and chief research officer positions at Stony Brook University. Dr. Hsiao has achieved national and international prominence and has a distinguished reputation in polymer science. He's published over 600 peer-reviewed scientific papers in addition to books, chapters, 232 proceedings and preprints, and he has more than 25 pending patent applications. So we're very excited to have him here. And Dr. Hsiao, it's all yours, please.
Okay, thank you, Arjan, and thank you. Thank the center for inviting me to give this talk. So today I actually I modified my title slightly. Talk about my journey in this whole water purification business, and so it started about probably 20 years ago. One was a polymer scientist, like Arjan was mentioning, and I came across a techniques called electrospinning techniques to make nanofibers. This is a very old process, back into 18th centuries, and French farmers, as you can see, using a jet or some sort, using electrostatic interaction to make aerosols. And aerosols is mostly to kill all the bugs for fruit trees. And this techniques actually was developed probably about 25 years ago or so to make nanofibers materials. How does it work? So if you have a polymer solution, that means polymer dissolved into a solvent. And if you're putting charge on this jet, and so this polymer solution will be charged. And during this charge, you have solvent evaporation. The charge repulsion becomes stronger, and you have polymer solutions becomes very concentrated. It will transform from the steady spinning to this unstable spinning, near a fraction of speed of sound. Of course, there are many parameters you can control this, from materials to concentration, to charge density, to surface tension, etc. So during that period of time, we're very curious about this technology to make nanofibers. So this is in 2000 in my lab. We start actually experimenting and using polymer solutions to make nanofibers. So of course, we're consider the application of these nanofibers. The first thing we're trying to do is actually try to make tissue scaffolds. But again, that my lab were not biomedical labs, and we find out some scaffold is great to form the tissue parts, and some is impossible. And we're actually taking an interest in this impossible materials to form the tissue scaffold. Turned out to be a great membrane materials. So during that period of time, I also start working on the membrane technology, and this is a picture illustrated by Dow Chemicals. It turned out this membrane technology had not changed since 1970s or so. So typical membranes technology is you have this non-woven backbone, and you have this porous membrane, which is about 40 microns. You add this part, this is called UF layer, and the pore size is usually is about 3 to pore size is about 10 to 100 nanometers. So and once you add this, probably 20% of the materials compared to the rest, your value increased by about 1 order of magnitude. Then all of a sudden, materials become much more expensive. And but this is only for ultrafiltration, and to make it into nanofiltration or reverse osmosis, so you coat a very, very thin layer of cross-linked polyamide film on top of it. And pore size can be less than 1 nanometer, so you can remove salt ions. Then all of a sudden, there's a very thin coating, and will increase your price point by almost 2 orders of magnitude. So immediately I realized that there's something about nanofibers, because if you add something nanoscales on the surface, very small amount, you increase the value of this membranes by almost orders of magnitude. So with this principle, my lab started working on this nanofibers membrane. This is from the simulation that we experimented. We decided to just look at the non-woven format, the cheapest format that we can get. And this is a simulation with 20% of solid, 80% of voids, porosity is 80%. If we have a way to divide this fiber diameter by the factor of 3, by factor of 10, there's still 20% solid, 80% of voids, then all of a sudden the pore size is much smaller. So if you take a section of this will be a very good coating layer. And the value of this membrane, it would increase by orders of magnitude because you can filter a much smaller size. In principle, you can do this. If you have a techniques or process, you can divide this fiber diameter by the factor of 10 or so. Then you can make a nanoscale membranes. So with this concept, we made membranes out of 3 different fiber diameters. One is a non-woven. The middle layer is this electrospun membrane, and there's the top layer. Electrospinning process is not suitable to make membranes, fibers that with diameter less than 100 nanometers or so. So we came across with a technology, which I'm going to talk much more. It's called nanocellulose technology, which we can make 5 nanometers fiber diameter. So we actually made the 3 layers of fibers, and for water purification. And through this research, we also realized there's an experimental rule that with a fiber diameter, plot that against the maximum or mean or average pore size of this membrane. This seems to have a rule that is mean pore size is always about 3 times of a fiber diameter. A maximum pore size is about 10 times fiber diameter. So you can control your fiber diameters by control the pore size of the membranes by your fiber diameter. So this is actually a breakthrough finding. So with this findings, we decided to actually start generating some larger scale membranes and try to see if they will can make nano fiber membranes for water purification. So we start focusing on ultrafiltration system. So this is a support with non-woven support, and this is a multiple jet electrospinning process. The principle is exactly the same. So we start making platform scaffold for ultrafiltration system. And with this technology, actually we spun off into two different startup companies. One is called Liquidity. Actually, they produce a in between ultrafiltration and microfiltration membranes. But since the porosity is so high, over 80%, so the flux is very high. And so they can actually using the gravity to remove most of the pathogens with a particle size larger than 0.2 microns. In addition, we can also use the surface to absorb some of the chemicals on top of it. So this startup company is actually making something very similar to LifeStraw. It's much cheaper and flux is higher. And actually, this company's product is Naked Filters and won this TechCrunch 2015 award. And for ultrafiltration membrane, typical smallest pore size will be probably less than about 10 nanometers or so. So for electrospinning membrane, this is the electrospun scaffold. We're not able to accomplish that. So this is where we start with the nanocellulose process. Nanocellulose is a nano fibers that made of any biomass that we can extract in. And the fiber diameter is in the range of maybe 5 nanometers or so. If you remember my 3-to-1 rules, that means the pore size will be probably about 15 nanometers to 20 nanometer range. And that's probably a very good range for ultrafiltration membrane, which we actually make a system like this. And indeed, we use the molecular cutoff experiment. Molecular cutoff means we use some micromolecules of different molecular weights, and we use a dead end filtration, and to compare with all the flux with the different molecular weights, we can convert the molecular weight back to the pore size. It's a simple conversion between the radius gyration and molecular weight. So we estimate that at the 90% rejection rate, we have pore size about 21 nanometers or so. So because the porosity of this membrane is very high, it's 80%, which is significantly higher than the typical sponge-like membranes made by phase inversion process. So the flux is usually can be 1 order of magnitude higher, and PM10, PM400, they're all commercial membranes. The rejection rate is about the same. So it's 11 times higher than this is a PNA-based membrane with a comparable rejection ratio. So this becomes a very high flux membrane. This is a oil and water emulsion. We use this membrane. We can completely remove the emulsified oil droplet, since the surface coating is nanocellulose. So they're very, very hydrophilic. So the fouling ratio is also becomes much less. So actually, this techniques allowed us to develop a large nanofibrous membrane production facility in Shanghai in 2013. So this facility is the facility that is started from my laboratory. It's this multiple jet process. So right now, actually, this membrane is a commercial product. So what does that have anything to do with the nanocellulose? In 2009, and when I was the chair in the chemistry department, I got invited by Richard Leakey to visit his research site in Kenya. And his research site, TBI, is actually right in here in this lake. This is Lake Turkana, which is a brackish water lake. And this is his compound in TBI. And this is the river, not the lake, but close to the lake. And this is Turkana Basin Institute. It's an amazing structure because it's truly in the middle of nowhere. It has no electricity, no running water, no internet. So everything has to be developed and by ourselves. And as you know that Professor Richard Leakey passed away early this year, so it's a great loss. But his vision was quite infectious, so I still haunting me and about the research I decided to do. So TBI does offer drinking water to local people. Those are the village people, and they carry a bucket of water. They walk for an hour each way to bring the water home to drink. And so Richard asked me whether I can use my nanofibers technology to help those people. And then I thought about it, and there's no way the electrospinning process can generate any kind of meaningful product to help those people. This is actually one of the pictures that we took with a local village. And one thing that impressed me the most is actually how resourceful people are and how much biomass they have. And the whole hub is actually made of biomass material. It just happened that the materials for the top coating layer, I was using the nanocellulose, which I purchased from a company to do the coating. So I start to take interest in this nanocellulose from biomass. And if you look at any biomass, this tree, it can be non-woody biomass as well. If you look at all the plant cells, you start breaking them down, and you find out that actually the typical photosynthesis is you generate a cellulose polymer chain, and they aggregate into this microfibril, which is nascent crystal. And this is one of the cellulose chains, and in between this cellulose chains, you also have hemocellulose, you also have lignans try to bind this together and form a larger plant. And in 2018, there's actually a very good articles and talk about this nanocellulose for water purification, and it can be used as a absorbent membrane materials. Of course, that's one area I was using it, flocculant, and you can also carry different catalysts. And the catalyst can be a photocatalyst for degradation of some sort, and all those for water purification materials. Of course, it can carry other metals and such as silver and it will act as a disinfectant. So it really has a tremendous value. And how do you make nanocellulose? Typically, you have two ways to do this. One is top-down approach. This is called cellulose nanocrystals or cellulose nanofibers. So how does it work? You take a biomass, treated or non-treated, and you're using chemistry. And chemistry basically allow you to degrade all the lignin part or hemocellulose part. So it's called pulping process. But the better chemistry is actually also further allow you to oxidize the surface of nanocellulose. Why oxidation is so important? Because oxidation will convert the hydroxyl group into a charge group. So one of the more famous processes called tempo chemical treatment. And because once you have a charge on the surface, you can use a very low mechanical energy to defibrillate them into nanofibers suspension. And I'm going to talk more about it. And you also have some process and you will not generate too much charge particles. So usually you use a higher mechanical energy. And of course, you know, after the trip to TBI, I always want the lowest mechanical energy, the cheapest ways to treat these samples to perhaps make some difference for the people who live in the off-grid community. Another process to make nanofibers is bottom-up approach. That means this is a bacteria growth nanocellulose. Is using bacteria and to convert the typical sugar, water, sugar solutions and make them into a nanofibers. Of course, the process of this is much more expensive and less appealing to me because we start competing, taking food away to make this nanocellulose. And this is the chemistry that with tempo oxidation method, about 2010-ish, this is a famous work. This is a cellulose surface. And as you can see, there's a hydroxyl group connected to methyl group linkage right here. And there's two shorter hydroxyl group here, but this one is a little bit more sticking up there, more hydrophobic. So they can be selectively oxidized by this tempo-mediated oxidation process and become COONA. This is actually a salt. In the water, this will be dissociate into negatively charged and positive charge. And the charge turned out to be very, very important. And this is just the process of the tempo oxidation method. And my lab, we start working on this tempo oxidation methods for about 2 years. Although that we learn how does it work, but the process never interested me because all those tempo agents and they're expensive, needs to be recycled. So I always thought about the people in near TBI, and there's just no way I would use these chemicals to generate any of the nanocellulose materials for them, just not a sustainable practice. Until that, I come across with, I recruited a doctor, Priyanka Sharma. She is from Hyderabad and from the National Chemical Institute. She was working on the different process called nitro-oxidation process involving using nitric acid and sodium nitrite and to extract cellulose from the raw biomass. She did a PhD thesis on making different nanoparticles. And I got really interested in this process because nitric acid, sodium nitrite, they're all ingredients to make fertilizer. So I thought that if we can use fertilization chemistry to actually extract nanocellulose, then the effluent or waste we can convert back to fertilizer. So that would be zero waste. And so I hired her, and jointly we developed techniques to actually extract nanofiber from almost any kinds of biomass. So compare with the typical tempo oxidation method. This is conventional pathway. First, you pulp the materials, you bleach them, you carry out tempo oxidation method, mechanical treatment to get nanocellulose. The unique feature of this nitro-oxidation method is we're using fertilization chemistry, nitric acid, sodium nitrite. Just one-step treatment may be a very mild mechanical treatment. We can also extract carboxylated. Carboxylated is important because it's negatively charged, will stabilize these materials in suspension. And the beauty of that is it can really, is ideal to extract nanocellulose from any non-woody plants, especially those underutilized, like agricultural residues, like agave, switchgrass, all the way to bamboos. Because all the higher plants, woody or non-woody plants, they have exactly the same cellulose nanofibers or microfibrils structure, because they're using the biosynthesis using similar enzymes. And the reason that this chemistry will work very well with the raw biomass, means you don't have to pulp them, is because nitro oxide can react with the major components in lignin, like syringal units, and they become soluble. And also nitric acid can degrade this hemocellulose. So this is all well known for quite some time. We just try to combine the previous knowledge, and it turned out this nitro-oxidation method can be utilized for any biomass. We have tested 16 different raw agricultural residues. This just to show you, this is nitro-oxidized CNF cellulose nanofibers from sorghum, from maize, from beanstalk, from millet. And length is usually pretty long, and the width is pretty small. Of course, once you use more harsh condition, the width can be even thinner, length will also degrade. But we're mostly interested in this zeta potential, which is negatively charged, because negatively charged materials were, number one, stable in the suspension. Number two, can be used immediately to remove the positive charge contaminant. So, with the support from National Science Foundation, we actually built a scale-up process. This is a 20 liters reactor, and it consists of 5 different parts. And right now we actually know that probably about 3 different parts are needed, so we can even further reduce the cost of this scale-up system to actually treat any of the feedstock, including newspaper or cardboard boxes. And so just to demonstrate, and on campus we have lots of agave plants, and for it's without any use, just to look good. But in the winter, usually the campus keeper will cut down all the agave and just put on the sidewalk. And these are the feedstocks. We actually, our lab just, took bags of agave cut from the campus, from maintenance group. We actually use our nitro-oxidation method, and we can extract very high level of NO nitro oxidized nanocellulose with a very, very high carboxylate content. The degree of carboxylate content depends on the chemistry. And the beauty about our process is really a zero waste process, because after the treatment, we separate the solid part is nanocellulose, the liquid part is the effluent. Effluent consists of still nitrite, nitrate, and also degraded cellulose, degraded hemocellulose, lignin. So we convert them back to, we can neutralize them back to this salt. And the salt is very much similar to inorganic fertilizer salt, except that they also consist of 30% organic compounds. So it actually give you a slow release fertilizer process. And the solid part in the suspension we use as a coagulant. We can, it's negatively charged, so we can remove, for example, all the positive charge contaminants, cadmium, lead, Ti, uranium. And once you remove them, they will coagulate. And then once they coagulate, you can use very low energy microfiltration to remove these materials. So it turned out to be a very efficient way to remove this. And for longest time, I always thought that in the wastewater, the ammonium parts, typically from urine, if you can do a phase separation, is a way we can actually recover this ammonium as a upcycle of all the nutrients. So we actually try to use our negatively charged nanocellulose to remove ammonia materials and to recover this material. So we have a patent application, but this is just to show that the removal capacity of our NOCNF is pretty high, not as high as synthetic hydrogels, but it's high enough. But these materials can be reused as a fertilizer as well. It's really good for fishery or wastewater treatment. So also after the removal, the ammonia absorbed microfibers, and it turned out to be it's a wonderful fertilizer because it really has a sustained release profile. So, and this is a starter. This is our ammonia absorbed microfibers, nanofibers, and control. Control means there's no ammonia at all, just the nanofibers. And we actually find out the microfibers performs the best. And the reason for that is because the nanofibers sometimes can be lost in the soil. Microfibers really give you a controlled release profile. So currently we're working with a local hydroponic farm to actually try to see if our effluents can be directly, not even neutralizing, and can be directly doctored and convert into liquid fertilizer for this vertical farming process. And the solid product can be again, reformulate and remold them into hydrogel-like materials for seed germination process. And this is the farm, and this is one of the projects we're trying to propose to have a very tight water and food nexus for the Governor's Island project. And in our view, that we can really use this nitro-oxidation process to have a circular design of taking the waste or residue from agriculture and modify them, and then use it to remove excess amount of ammonia or even nitrate. Nitrate is negatively charged, so we have to convert our system into positive charge, but that's not so difficult. And we do have a project using inorganic nanoparticles attached to the nanocellulose scaffold to remove nitrate. And finally, I want to just, this is near the end now. This whole project is supported by National Science Foundation, DMR, Eager Grant, PFITT, and I-Corps. And this is the current team working on this nitro-oxidation process. So I hope I give you enough insight into my journey, how start with polymer scientists making membranes to working on biomass feedstocks. And I was asked to post 5 questions. Think about what this process NOP will lead to, and so I always want to think big, and so I want to tackle the most common global water pollution issues today. I think that is probably the wastewater nutrient recovery in my mind is high on the list. And what are the most cost-effective technology to treat about global water pollution issues? What are the most cost-effective technology that can provide drinking water solutions? What are the most abundant cellulose biomass sources that are underutilized or not being considered today? What may be the major hurdle to use these underutilized biomass to provide sustainable drinking water solution? So, and this is just my own journey. So I'm going to stop right here and be happy to take any questions. Thank you.
Well done, Ben. That was great.
Thank you.
Thank you so much. Super impressive as well. Well, I mean, well, it's very, very impressive. But yeah, and so I guess I'm most interested in the just thinking about the center and the work we do with wastewater is the ammonia absorption. And I guess one thing I'm curious about there is that is the extent to which, in that case, that the microfibers are used as added to a solution and then recovered, versus the idea of actually setting up sort of like a filter and then the filter is recovered.
Yeah, my view is I'm trying to use the benchmark for me is activated carbon. And I'm very much like to pack, replace the activated carbon with the solid microfibers. Nanofibers actually does not work very well because it get lost.
Right.
Yeah. But microfibers, I think, can be used as a complement for activated carbon. But now all of a sudden we don't have to do a pyrolysis and activation. You directly just activate the raw biomass.
Yeah, I get, but I'm specifically now on the front of absorbing ammonium
Yeah,
in
yeah,
wastewater.
yeah.
And so, I mean, to what extent are those microfibers, you know, can they be, to what extent, so it sounds like you're saying they could be packed into like a column or any sort of morphology to absorb ammonium.
Yeah, I think the column will work very well. And was, you know, actually you and I writing this STC concept paper, I actually recruited this chief scientist in NOAA, the Sandy Hook, and they're doing the fishery. They have exactly the same issue with ammonia removal issues. And so I think I have actually also talked to Acacia ET. We're thinking about, you know, if you have digging a trench and just fill with this treated biomass, almost like a compost biomass, and run the water through it. And you can do a saturation, calculation. You can maybe even use Chin's method to measure the nitrogen level before and after. When it's done, you move to another trench of material, but take this materials and use it as a soil amendment or fertilizer supplement.
Sure. Yeah.
It's much cheaper. I think I'm not done the cost estimate yet. I think in principle it should be much cheaper than the biochar.
Okay. Yeah, and you think scalable as well?
Well, that's how I try to learn how to scale up. I think the issue is how to handle larger quantity of nitric acid is the key, and we're working on that now.
Got it. Okay, well, I will probably want to follow up with you on this.
I hope you will.
Yeah, no, we definitely will, but I don't want to hog up things any further.
Yeah.
I'll cede the floor, but thanks so much.
Yeah.
Thank you, Ben. Maybe I'll go next. So I'm a little familiar with the kind of work that we do collaboratively, but for the participants' sake, can you talk a little bit about how you could modify these nanofibers to target other contaminants like PFAS, especially because that's of interest to the center, but also for the New York State and nationwide. So a little bit on that.
Yeah. PFAS is a tough one because it's negatively charged, right? They're nature positive charge contaminants like metal ions. That's not so difficult with these type of cellulose. They're natural cationic absorbent materials. And to convert the charge, the easiest way, of course, you can do chemistry. But the chemistry, you're talking about sustainability issue. I think the easiest way for us to do is going back to metal ions. What type of metals? I think higher the valency, the better it is. And so I'm designing using different micronutrients is metal ions to. It depends on the stage what I want to do. Calcium is good, magnesium is good for germination stage. Aluminum is very abundant in the soils, the most abundant metal element in the earth crust. So that's a good one. And the zinc oxide, of course, for flower stage during the farming is also very important. So, and we decided to just launch a program, try to understand how do we absorb and grow metal oxide nanoparticles that can be also used as a micronutrient to therefore remove nitrate. And PFAS is very interesting because I don't have to worry about the food growth with PFAS. I think we're learning, I think the higher the valency, the better it is for not for sulfonated end groups, but for carboxylated end group. Even silver may work too.
Yeah.
Yeah.
That would be a pretty expensive treatment system with silver, but yeah. Yeah.
But if you only use a very small amount, you can also recover it, reuse them.
That's right. Yeah.
I don't know. Lots of things to study.
Thank you, Ben.
Yeah.
Are there other questions from participants? You could either unmute yourself and ask the question, or you could type in the question using the chat option.